Welcome everyone to our first meeting of the year, Orlando Python, and we're going to look at a library called RocketPy this month that allows us to design, build, and test out hobby rockets. So we're not talking the SpaceXs of the world. We're talking about the small hobby rocket. I just searched hobby rockets just for a sense of scale. We're talking these things that you can launch in your, well, maybe not your backyard, but things you can certainly hold in your hand. You're going to mount them on some sort of launching apparatus, launch stand. They'll go, however high in the air. I would say a decent size without getting too crazy. Probably go maybe 1,000 feet into the air, maybe 2,000. So that's the kind of thing that we're going to be using this library in order to create. Now, RocketPy has been around for a couple of years at this point. You can see they're not quite to version 1.0, so there are still some things that the maintainers want to put in here. But as we all know, version numbers are completely arbitrary. So, take it as what you will. What this allows us to do is use Python to completely simulate everything necessary to calculate trajectories that are pretty accurate. You can see just based on their documentation here, not only do we build the rocket, so having the rocket motor, the nozzles, parachutes, nose cone, how many fins you have on there, to design the rocket, but we'll also be modeling the environment. Now, a cool thing, and I looked into this library, you don't need to know all of the information to model the environment. You actually can just give it a date, the time, and coordinates or some other means of location, and it actually goes out and fetches all of the weather conditions at the time. So you can model predictions someday in a day, however many days in the future, and you can also have it model based on any records of your flight in the past to just see how could you have made a previous flight better. It takes all that information and determines or models a flight with all of this, including all of the data that would be gathered if you had sensors on the rocket. And finally, it puts all of that together in graphs and analytics to show you what the simulated trajectory might look like. Now, one of the cool things with this library is that everything is in code in one way or another. So you can see here just with the environment, we're giving it coordinates, what's the altitude of those, the dates, like they say, you can do dates in the future, dates in the past. There's also this rail length, and that's just the stand that your rocket is sitting on, because that actually does, we'll see a little later, that does matter for these rocket launches. Creating the motor, and we'll talk a little bit more about this thrust source when we get to it. Designing the rocket, so how big is it? How much does it weigh? Where are the how is it mounted to your launch rail? The nose cones, how many fins you have, things of these variety. We can even add parachutes, like a main chute and a drogue chute, and that's important because if it's windy, it actually will tell you, here's where things is going to land. And then all you do is you have it fly with this information, and then it will output a ton of information. You do all info, you will be getting way more information than you could ever hope to use, and way more information than I know what to do with when looking at this. So this is a little preview. I've already gone ahead and downloaded the source repository. You can do a pip install, provided you have the other files that you need in order to run this. But I've downloaded the source because they have their own data sets that we can use to follow along with the getting started and some of the other pieces in the documentation. However, if you want to follow along or you don't want to worry about setting things up on your local machine, the first badge on here is Open in Colab. This will open up a pre-configured environment in Google Colab where you can run all of this in your browser on your machine. If you're just interested in trying this out and, and seeing all the pretty graphs that it produces, highly recommend you take a look at that during the talk and afterwards. It's really easy to get started with. So with all of that in mind, go ahead and share the screen because we're going to be going back and forth between our documentation here and some code. Actually, I think we can just stay in the browser. If I'll just do a Jupyter Notebook setup. Let's see. So I'm just doing Jupyter Notebook. If you are not familiar with that, Notebook allows us to run code locally on our machine, but it provides a UI in the browser. I'm going to create a new notebook here. And we get started. This just launches if you have Jupyter Notebook installed. All you need to do is in your command line, you just do Jupyter space notebook. It opens it up. It's really nice if you are doing any kind of data exploration like we're about to do here. Looking back at our quick start here, everything that we start to do, we've already installed RocketPy. It is just a pip install RocketPy. It brings you everything or almost everything that you need. And the reason why I say that is that thrust source that we will get to very quickly here. Okay, in our notebook, and if you're not familiar with notebooks, these are different cells that we can create. You saw me switch it from code to markdown. You do RocketPy Orlando Python, and boop, it's just inline, really inline documentation for what we're doing. So the first thing that we need to do is import our components. This is a code block. I do shift return, and we have now run this first thing. For our, the first thing that we're going to do, we're going to set up the environment. Now, in their example here, they've set the rail length. They're giving it coordinates, elevation, and a date. Some of these are not required. I believe in here, if we do help environment, oops, this should, yeah. So this gives us a nice output. So you can see here that technically the only thing that we actually need to supply is rail length. Oh, and by the way, help is one of these Python built-in functions. This works even inside of a terminal, which is great. However, if you are in a terminal and you need to get out of it, you got to press Q, and it is non-intuitive. Command C does not, or Control C does not work. So we can see our environment. We'd have to give it a rail length. It assumes we can technically try this on different planets to see the gravity. If we're going to run this in Orlando, we'll need to figure out our latitude and longitude. The date, I believe, defaults to whatever the current time, date and time is here. So let's quickly just go. Let's say we're launching this at Orlando International. So KMCO coordinates here. So grab this, and we can pop this into our environment. Quickly see, yeah. And I'm going to keep the same capitalization that they have in their documentations. Personally, I prefer to do lowercase as standard Python dictates, but let's just keep up with their documentation here. So we're going to create our environment. The first, as we see in our help string here, we need to give it a rail length, and we can give it the same 5.2 that they have in their documentation. However, now we can come to our latitude and longitude. So latitude and longitude. Latitude, longitude. And we don't need to do anything else. It will be today's date. Elevation here is basically 0. It's like 50 feet or something like that, but this is basically 0. Create our environment, and here we go. Set atmospheric model. So I'll just copy this over. So you can see here, this is now what we've created the environment, given it its location. This set atmospheric model is going to go out and grab that the weather, things like the winds aloft and all of this other good information. It's using a forecast model, and GFS is one of these atmospheric models that that NOAA and was it National Academy of Sciences, one of these governmental organizations produces. It's actually being phased out for something called NBM, but is not necessarily important for this particular application. So we can see, oh, it's running, or maybe not. Please specify a date. Oh, okay. Let's specify a date in here. Let's see. Yeah, so if it wants us to do that, I'm going to go ahead back here and do from date time, import date time. And then we'll do date equals date time dot UTC now. Maybe. Argument after. Oh, did it do yeah, so they passed it here. A tuple of year, month, day, and hour. However, their documentation, they wanted a date of type date time, which, okay. So date and date time. So we got 2022 and today's date, and let's say we launch. Well, I think 23 would be either 7 o'clock or I think it's 7 o'clock maybe UTC. Oh, never closed. Well, call me crazy. I'm almost just curious. Now, it says forecast, but when all else fails, I will just copy the code in there and go ahead and update the latitude and longitude, because that's really the only thing that we really care about right now. Keep the same. And while we're here, we might as well just set a 50-foot elevation and get rid of this. So I guess we'll just do historic. Huh? Huh. Well, I am certainly very confused right now. Hey, that's the joy of live coding, isn't it? Well, we got on this page. I wonder if there was something different around here. Oh, yes. Would you look at this? So I know that I've been through this particular, let's switch over. It looks like their README might be a little bit out of date, apparently. They're doing env.set date, and that might be one thing that is giving us pause here. So we can keep the same environment. So this looks familiar there. However, let's go ahead and set our date using this method here. So let's get rid of this. We'll rerun this. Set the date. Okay, so that sets it there. And then finally, well, it's the same line here. So set atmosphere model, and hopefully this does end up fixing that particular issue. No, it does not. Net CDF4 is not defined. I am very curious. Well, to the internets. Dun, 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 dun. Net CDF4. I wonder. So I'm going to double check that this is saved, and I'm actually going to this is over in a different window, but RocketPy and was it net CDF for Python, I believe, just to double check. Yeah, net CDF4. And just double check that all that is in there. Relaunch my Jupyter notebook here. And just run through this again. Interesting, not an available data set, but at least it was there. So, well, we got something. And then I think it just was env.info to see what it pulled down. Here we go. So, okay, so something did work. We have our information about our launch site. So we have our coordinates as well as the date. Actually, the current date right there. So this would be tomorrow at noon UTC, so either 7 or 8 a.m. right now. And it was able to fetch the weather for us, predicted weather. You can see the wind direction at the varying altitudes, although this goes way higher than we're going to, for sure. As well as the density, because both of these are going to affect the flight and altitude that the hobby rocket can achieve. Okay, with that out of the way, let's continue. And I would like to close you, you're no longer active. All right. So continuing, and you can see same details here. Now that we have the environment set up, we need to create a motor. And this is going to be, personally, I have not used a commercial hobby full motor, but you can see the way that they're modeling it here in the code. This does refer to a particular model that you can buy. So we got this thrust source, and this thrust source is this graph right here. When a when you light a rocket, it's not going to produce the same amount of thrust as soon as you light it to when it burns out. That's what we're seeing right here. You see that you light it, you start at 0, it very quickly ramps up, and then it mostly levels off here, dropping over time, and then it hits a critical point after about 3 seconds where there's not enough to keep it the same amount of thrust up, but it's still producing some, and then just until 4 seconds after you start, everything is burned out. So we're looking at the thrust curve right here. And the way how this is used or ingested into the code, if we actually go here, the reason why I downloaded the source for RocketPy is not necessarily that you need to if you have all the information, but they include the data for a number of motors here, especially the ones that they have in their documentation, which just makes things a little easier for us. For example, in their documentation here, we're going to be using this Cicerone, I'm not entirely sure how to pronounce it, but this very particular engine right here. So that is in data, motors, and the name of the engine. So data, motors, and then we have a couple of built-in engines right here. Oh, and then the way that they look, these are these .eng files. They're just, see it, well, these are tab separated values, I guess, technically. But you can see at this many seconds is producing this amount of thrust. At this many seconds, producing this amount of thrust. And that's what this graph shows. So back in our notebook, we can paste this in, although this project is running in the root, so I can get rid of those. Now, this is going to burn out after 3.9 seconds, and I think this is entirely independent with what you see in the thrust curve, although it really should match. There are other things like grain numbers and density. This is giving you or giving the model information about the actual propellant inside of the motor itself, and there are a number of ways that you can get that. For example, there are some that are reusable, so you can buy it once, get all of the propellant that you need, and reuse it over time. Then we also have nozzle radiuses, the throat radius. Nozzle is the bottom of the bell. Well, if this were a really large engine, nozzle radius would be the bottom of the bell, and the throat radius would be the top. In theory, kind of like think of the book movie Rocket. Was it Rocket Men, Rocket Boys, that sort of thing. And we can actually play with this later to see to optimize, say, what the nozzle radius should be. I think that would be fun to look at. But all we need to do is create this, and just like we did with our environment, we should be able to do to see the info about it. And there's way more info than I actually know what to do with. Actually, no, that's later on. I keep thinking like, oh yeah, this is the one where I am so too much information is available. But you can see that based on the information that we gave it, is able to calculate the mass of the propellant, which will go towards the total mass of the rocket that we design, the exhaust thrust velocity, and then how much thrust we're actually getting from this for however long, and then we have the impulse in newtons. Okay, we have the motor, so just a single motor rocket. The next thing we need to do is actually to design the rocket. This Callisto refers to a particular hobbyist, off-the-shelf body that you can design. So we'll paste this in, and you see we are giving this rocket the motor that we just created. We're also saying here's the dry mass of the rocket as well as the radius of it. I'm not entirely sure what to do with the inertia numbers, and then these are offsets for the length. So from the center of your rocket, how far down, I believe in meters, is the nozzle, and either the bottom of the propellant or the midpoint, like the average mass center of mass of the propellant, I believe. We also have the power off drag and power on drag. These are the same sort of curves as we see here, but this is more what are the aerodynamics of the model rocket. And these are also in the built-in data set. Lastly, in this little bit, we are setting the rail buttons. And these are how the rocket is actually attached to the stand. So you remember, we set a rail length for the stand, and these buttons, we're saying, well, we have one button that is 20 centimeters above the midpoint, and another one that is half a meter below the center point, and that's how it is actually going to be connected. That matters later, because we'll see in the data when the rocket launches, we actually get some oscillations because of the asymmetric thrust and how it was held there to begin with. It's really cool that this library does that. I'm going to quickly check the chat here for a second. Like living on the edge with coding. Oh yeah, and then West, you're absolutely correct. I should have used West for the longitude. Oops. Anyway, we have this. I'm going to double check that we actually have that properly. Yes. Okay. Yeah. So we're West. Okay. So we now have the body of a rocket. That's just the central tube. We still need to add things like a nose cone, parachutes, and fins to this rocket. We can pop back to here, adding aerodynamic surfaces. So just as we said, we got nose cone, fin sets, and tail. So I'm going to copy all of this over and then talk about it a bit. So the nose cone, length about half a meter going up. This von Karman kind, there are a handful of different known and widely used varieties of nose cone. For example, I can just do say nose cone design, just to pull up a couple examples. So general design is simple conics, blunted, different shapes, more spherical there. They don't give, I don't believe they give a specific, they don't give anything more for the von Karman that they're using in there. But these are all different nose cones that you could buy from a hobbyist shop and build your rocket with. And then finally, distance to the center of mass. So center of mass of your nose cone there. Fin sets are also going to be, these are going to be the things that are on the top, giving a little bit of leading stability. So this one has 4. You also got the tail on the bottom, just to provide a little bit more of the stability in the bottom. So stability on the top, but you need a little bit more drag on the bottom, especially with these hobbyist rockets, or they tumble over. Larger rockets don't need it because they have many of them have high gimbling engines that actually will keep it in that nice sweet spot. So you don't have to have a whole bunch of fins on the bottom. But that's all that this stuff is doing here. And we just add all of that to our rocket design. I believe the last thing we need to do before pulling up some info is adding parachutes. I'm sure, yeah, I'm sure you're familiar with parachutes. If you have larger rockets, you'll have drogue chutes just to provide some extra stability in the air, but then they give way to a larger parachute. That's true on hobbyist rockets as well. You can actually see that. Well, so this one is designed the Drogue Trigger in this custom function. So there are a bunch of different things that you can do. Like this is giving you pressure as well as the location information about where the rocket is at any given time. These triggers here are just at every step in the launch. If you give me true, then I will deploy this parachute. So you can see for our Drogue Trigger, this Y5, Y0, 1, 2, 3, 4, 5, once our rate or if we've reached the top and our speed in the z-axis is now decreasing, it's going to automatically deploy the drogue chute in our simulation. So they're giving you all the information here to make your own things, but the drogue chutes are just going to be, as soon as you start falling, deploy the drogue chute. And for the main, once it starts falling and we are less than 100 meters in the air, then the drogue chute will give way to the main chute. That's all that these functions are doing here. And you can see it's really just the return line. These are just comments giving you what you need to make more sense of it. You could absolutely do pressure, like if you wanted to land on Mars, for example, you probably care way more about the density, the pressure of the atmosphere as you're coming in than necessarily the altitude. But it's here on Earth, it's really easy. We just say, hey, once you start dropping, and then when you get to 800 meters, so you can slow down even further. Same things here. Actually, it looks like, so we're actually just creating the same or almost the same parachute. So you can see our CDS is just how much air it's going to capture, kind of in a negative sense. I believe drogue chute is going to catch less, is designed to catch less air and slow the rocket down slower than, or no, sorry, I got the two confused. Main, it's going to catch more air. And I believe CDS has to do with, just how much air is able to capture, regardless of the size, its actual size. And then the drogue chute is, if this is linear, is going to catch 10 times less. Oh yeah, and don't run this multiple times because, if you are in a notebook like this, and you see, hey, we're building this up slowly, I can go back and I can, you can make changes and rerun all of these. But you have to make sure that if you have something like, I have my rocket, this is an object, it is its own thing, and every time that I run this, I'm going to keep adding nose cones. Maybe they have something here saying you can't have more than one nose cone, but if you keep adding more parachutes, it's going to add more parachutes. And they have a little warning about that right here. Yeah, so you can remove that as well. Finally, we have everything that we need to actually create a flight. So we created the environment, created a solid rocket motor, designed all of the other aspects of our rocket. We now have what we need to go fly out in the field at the location that we specified and actually fly this rocket. So we're going to create a new flight. Is the rocket that we created. We give it the environment. We're also going to give it an inclination and a heading. So 85, so it's going to be 85 degrees up, 85 degrees, so straight up, and then 5 degrees over. And then heading 0, so I believe this is going to be due north, 5 degrees ever so slightly in that direction. and it has created its test flight. And now, are you ready to be overwhelmed with information? Because there is a lot. We're going to do test flight. Let's do short. We're going to do the info, and then we'll do all info. So, wind speeds, rail departure state. And you can see, I don't think those angle of attack, static margin. Let's get back to this because you can look at this for the exact numbers, but the graphs do it way more justice. Burnout state, so burnout time was 3.9, as we said. Altitude at burnout, it got this got up to 645 meters. That's roughly a quarter of a mile. Yeah, so apogee. Oh wait, no. I got that wrong. So the rocket stops producing thrust at 645 meters. Its apogee, its highest altitude that it was able to get in the simulation, is 3.1 kilometers. With 3.1 kilometers after about 25 seconds. The lightning fast, really quick. We can see here are the events. So just dealing with the parachutes here. So the trigger, or our drogue chute, was triggered 1/100th of a second after it reached its peak. It took about a second and a half to fully inflate, and it was able to do it within 30 meters of apogee. And the main parachute was after about 2.5 minutes. So it got up there really quickly and took its time coming down. That's just to be expected. And we see that it was fully inflated after just 50 meters after it initially deployed, or we told it to start deploying at 800 meters, and it took about 50 meters for it to actually fully engage. And it impacted about a kilometer to, actually, I'm not sure which X and Y they're referring to here in terms of which is north and south. My guess, because we had it going slightly north, is that X, it went about a kilometer to the east and 1.7 kilometers to the north. And time of impact, it took 5 minutes for the entire flight, launch to end. And the velocity of the impact, it was traveling at 5 meters a second, which is pretty good. And then gives our maximum values. Okay. A lot of information, a lot of text. Let's look at all of the information, because that's where our fun graphs come in and where we get overloaded with information. All info. So we have all of our initial conditions. We keep coming down here. Now we have our pretty graphs. Take a look at this. So this is the simulated trajectory of the flight. Starting at our launch point here, we see it projected in, or simulated in 3D for us, but then you can actually see the X, Y, and Z graphs as well. So you can see it went up to about 3 kilometers, and that was mostly going due north here. We see that the green is a little further along because that's the inclination, or we had it inclined at that, but the wind affected it almost immediately. And we can see that after it punched through the lower levels and got through, the drogues immediately came out, carried it this way, and then there was a shift in wind direction towards the surface at about 500 meters that pushed it a little bit back towards us. So it went further than that, 1 and 1.7 kilometers, but the wind actually pushed it back towards the launch site. There's a lot of information here. picture is worth 1,000 words sort of thing. I find it fascinating, and you can see we're only a quarter of the way through. Trajectory, kinetic plots, the acceleration in all the different directions. So this blue line, I believe, is when the main parachute actually deployed. So you can see at the moment that it finally fully deployed, it put a lot of G-forces on the rocket, but not nearly as much, obviously, as the launch. That put a whole lot on there. Angular position plots. Okay, now this is cool. I find this cool. So this lateral attitude angle, if you imagine just looking at a rocket as it's going up, it's going to go up. But you can see that we have these oscillations in here, and without getting too technical in it, this really is the consequence of that rail that we launched from. The initial burn of a rocket motor, it took 3 seconds. So you can see we got time here. This is over just the first 26 seconds of the launch while it was going up. But this induced oscillation is caused by the rails. And there are the 2 buttons that we added early on. As the rocket is first lifting off and getting off the rail, it's mounted, or the thrust vector coming immediately down from the rocket is going through the center of mass, but it's to the side of the rail that we are launching off of. And when the first eye hook comes, or rail or eye hook or whatever you're using, comes off of the actual rail that it was sliding on, well, now it wants to try to turn, because this is now free, but the bottom rail button is still going, is still on the rail. So as it comes off, it's actually going slightly back towards the rail. Once the final button gets off, it is now free, or the fins are now free to provide the actual stabilization. And as it swings back and forth, that's what we're seeing here with these oscillations in the attitude angle. And it's really, I find it fascinating. And that's the kind of thing that you can play with in here, and to see, well, based on the size of my rocket, the thrust of the motor I'm working with, can I position the rail buttons in a specific location to reduce the amount of oscillation and improve the efficiency of my rocket? And this is just one of the many things that you can do by just plugging all the information into this library before going out. You may not even know that there's an optimal position for that if you just build it and just see what happens. And Euler precession, there's so much more information than I know how to use here. And there's even more pronounced angular velocity. They just look at how much a huge amount of oscillation immediately coming off the stand, and then it dampens as the aerodynamics come in. Going further down, aerodynamic drag force, drag increases as airspeed increases, and obviously, if I remember correctly, the burnout time, the burnout time was after 3.9 seconds. So at 3.9 seconds is seeing the highest level of the atmospheric drag. And then after that point, it starts slowing down, and it gets here where it reaches its apogee. All these things. Angle of attack, as you can see, the oscillations, stability, frequency response, and way more information than I know what to do with here. But it's I find it fascinating that we just did all of this in relatively few lines of code, Certainly less than we would need to do if we were trying to do this on our own. But that's not even the coolest part yet. So before we get to that, check the chat again. So Jerry's saying when he launched model rockets as a kid, would so gluing lengths of soda straws to keep it on the rail. I remember doing that in school too. Certainly need a little more strength for these with while limiting the amount of mass. That's also very important. So does the code produce a bottom line message to see if the launch was successful or not? I'm curious. So if there is something simple like that, we created a test flight. That's what it is. So let's pull this out. Okay, they don't give us anything special. Let's actually see what is in this test flight. Flight phases or Mach number, Arnold Reynolds number, time codes. So if you don't know what I just did here, dir is a Python built-in that prints out to your console or whatever you're working in all of the properties and methods of the object that you give it. So this test flight, just for example, I can do test flight, was it dot angle of attack? And okay, so that tells me it's a function, but if I give it a time code, it will give me the angle of attack at that time. But yeah, it just it spits out a list of all the different things that you can access. So maybe a little, okay, that's not too bad. Calculate flutter, got all these. There's our environment that we passed. We can export pressures, what the heading at a given time. There's info that we called earlier. I don't think it will give us like was your launch successful. Now if you look at the graph and it gets it I mean, if you look at the graph and it goes right off the launch stand, I would say that's not a successful flight. You could, if you wanted to make it in an automated fashion, like was this even a reasonable flight? You could see something like, is the time of impact of my flight greater than the amount of time that the rocket motor was supposed to burn? I would categorize that as the minimum of a successful flight, because if it hits the ground before your motor stops running, then you know you had a problem. Yeah, so there's a bunch of other things that we got that are part of this that go to make all of these graphs. Okay, would it be reasonable to build a model rocket down to scale of a modern rocket like the SLS or Falcon 9? Absolutely, yes. People do this all the time. I just with the model the hobby rocket image search has one pulled up a Saturn V. I've seen videos. Let's just do let's do Saturn V hobby rocket. Some of these can get pretty crazy, and as Jerry says, they're I don't actually think anyone, maybe the FAA does have the hobby thing. It has to be below a certain weight, and then there obviously are airspace concerns with launching these things, but if you want to make one, you can make it. You make it and have it do whatever you want. Also, there's a Lego version of the Saturn V. It's fantastic, highly recommended. But I've seen multi-stage rockets where they'll launch thing, separates, second stage starts running, and then it's all sorts of fun, all sorts of crazy. I know for a fact, like thinking about the FAA, and I don't think it's the TSA. I really think it's just the FAA, because even the FAA also is also involved in spaceflight. I can think of SpaceX right now, where they're doing their larger rocket tests, like with the BFR or Starship or whatever. They changed the name at 3 or 4 different times now, but they actually need to request launch permission from the FAA for their test flights. And the FAA actually got a little bit on their case somewhat recently, because SpaceX messed something up, or they didn't give them all the information or something like that. But for a hobby rocket, you actually have to be more, unless you have so much money, you're going to put something in that gets over probably a pretty, or not that restrictive of a weight class. You have to care way more about the where you're launching in terms of airspace. I put this at Orlando International, just because if you're launching there, you probably have permission from the tower and whatever you need. But if I launch right here, technically, I can't even fly. I can't fly a drone above 400 feet here, because that's where Class G airspace ends, and anything above 400 feet over most of the United States is controlled airspace in one way or another. But especially in Orlando. Orlando has something called a Class Bravo airspace for Orlando International. It's custom tailored. It looks like a reverse cake. It's a big deal if you mess with their airspace. It's a really big deal. So we launched. We built a rocket. We launched a rocket. We saw all these wonderful graphs. Now let's just talk a little bit about, they have this other thing here, using simulation for design. This is the part where you can take all of the things that we just did, and we can design our simulations to test various configurations and see what the most efficient one is. Just for example, in their documentation here, they're looking at comparing the static margins of fin positions, and it, for the various factors in 0.5 up to 1.3 and steps of 0.2, is just creating, it's removing the previous fin. It's creating a new fin with this particular one. It is creating a test flight with the same information, the same environment, same inclination, same rocket, just changing the type of fin. That's doing post processing, and then adding the simulation results to the final graph. And for me, I'm not entirely sure what I'm looking at, but it kind of looking like this. So is it the attitude angle in the offset here? You want to minimize the deviation of the attitude angle in order to make sure the rocket is pointing down, or is pointing perfectly down for as long as possible. And to me, that tells me that this blue line, because it is maxing out. Well, actually, so this is kind of interesting. I'm not entirely sure what the most optimal thing to be here would be necessarily, because this bottom one it's more extreme. So you can see that this is coming down to about is it 7.5 degrees from its desired inclination from that initial oscillation off the stand. However, it maxes out faster than the blue line, which is objectively better. But I wonder if this graph were to be extended out, which of these configurations would dampen out faster? I don't know. But these are the kind of things that you could run these simulations about, and then actually use it to inform the design of a rocket. That, okay, I can run all of these simulations effectively for free on my machine, which is way cheaper than getting a bunch of different rocket components and flying out and just seeing what the best one is. So I am curious how much of this we can. I don't think we can really copy. Everything down to this point is the same thing that we've been doing. Don't really want to copy. I kind of want to look at the rail buttons, just because we talked about that plenty. So let's just jump into that. We got 24 minutes left of just our normal time period. I am curious. Okay, so we have a Callisto.set rail buttons. I bet there is a remove rail buttons, and we can check that by running dir on here. And so we got add nose, add all of that. Well, I actually don't see. Okay, well, we got add pair. There was add parachute, and there was a thing to remove the parachute. Oh, set rail buttons. We can let's see. Callisto. Actually, let's do help. Callisto set rail buttons. Add a rail button to the rocket, allowing for the calculation forces exerted by them. Da 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 da. Okay, so this probably will be safe to just overwrite the values. So from here before, when we ran this, they had set rail buttons at 0.2. There, I'll just paste this down here. So if we treat this one as the fixed point, I bet we could do something like let's say 4 point in range. Let's do 0 to non-inclusive 0.6 in steps of 0.1. So we're going to get 0, 0.1, 0.2, 0.3, 0.4, 0.5 here. And we'll do Callisto.sail rail buttons, do point. Now it would come in and do the we would create the test flight for it. And we'll use the same conditions as we had before. So we had, was it 0 and 85? Do print, and do launching with top rail button at points. So we get a nice print statement there. We create a test flight with the current rocket configuration in the same spot. And now for actually extracting the information, so we got here. So I guess post processes the function that the info and all info call if it hasn't yet been configured. Now they're doing static margin at ignition. So these are actual things. I kind of wonder. Well, let's look back. We had information about how much oscillation there was coming off of here. So we had rail departure state. So rail departure angle of attack. So at the point at which it came off of the rail, our rocket was was deflected at its maximum of 13.7 degrees. So I bet if we just do a rail departure, let's see here, I'm going to input a cell. Is it insert a cell above? I'm going to call deer on test flight. I think we already looked at this, but let's find the actual function that it calls. Was it? Oh yeah. Well, it was angle of attack, and yeah. So we're going to have a let's see, max deflections is an empty list. So we're going to max deflections, or yeah, max deflections dot append. It's going to be the test flight dot angle of attack, but then we need to figure out at what time it left the rail. Was it max rail buttons? Total pressure out of rail time. That's it. So we do test flight dot out of rail time, and cross our fingers. Float object cannot be interpreted as an integer. Oh, could you not do? Let's quickly look. We got Python range floats. Oh, so they're pulling in NumPy. Well, you know what? I know something else we can do for that. We're going to do between 0 and 6, and then we'll just do point, or let's do numerator, and then we'll divide it by 10. So our top point is going to be numerator divided by 10, and that will give us the same steps there. Rerun, launching. So we are now simulating a handful of flights with these different rail positions. Encounter to divide 0. This must not contain not a numbers. Well, let's see. Let's see what got put in max deflections. Well, it looks like it was. I guess. Oh, it must have had something it didn't really like in the last one there, because of the 6 that we were supposed to run, it only gave us 5. But you can see that as the distance that we went up from the rail, the maximum deflection increased, and that makes sense because we're getting further away from the bottom one, and that gives the rocket more time to start bending over. But what's not shown here, and I'm sure if we really wanted to go through and look at all of the graphs, is let's say, actually, we can rerun this. So we got max deflections, altitude. We can see what how this affects the max altitudes. So altitude. Oh, I just did altitude. Let's change this. Max altitudes. Do this max altitudes dot append test flight, and I'm sure it's in one of these max. So we got max speeds, max acceleration time, total pressure. Oh, it's probably under apogee. Yeah, okay. So then we just add apogee to this. And I'm forgetting how to spell it. Yeah, apogee. So let's actually whoops, I accidentally restarted the entire kernel. Womp womp. Well, I was just going to change that to 5, but now need to run some things again. Oops. Let's just run the things that we need. We need our environment set up, downloading the model information, and it's done. We need our motor, our rocket set up. We don't need to run those test flights, so we can just come all the way down here to our simulation now and start rerunning these. So launching with the top rails, and this is, we're going to stop one short than we did last time. All right. So our max deflections are all the same, and now we can check our max altitudes. So adjusting the rail buttons isn't giving us that much more altitude, but you can see that just by reducing the distance between our top and bottom rail by going from a full meter on the furthest to just half a meter, we're actually getting an addition, just over an additional 2 meters in height with just that small thing. And Jerry has pulled up a link for us so we can actually see what these rail buttons look like. There we go. So standard rail buttons, yeah, so they would fit, well, put them in there. This side, goes inside, screw them in, and then this would slot into what is effectively an I-beam for the rail. I'm curious if they actually show us one. Yes. Oh, not an I-beam, but yeah. So these would just slot in there, and again, as it's coming out, the greater the distance between these rail buttons, the more time it has for that other rail button to start sliding over because of the asymmetric thrust and single point of, or the now single point of friction for it to start turning over in split second when that motor starts. Anyway, to wrap up, this is a fascinating library that is doing a lot of heavy lifting for us. Who doesn't like launching rockets? And you can launch them on your own computer, and maybe it's not as fun as Kerbal Space Program is necessarily, or going out and buying and building your own and finding a place to launch it. But you can play around and optimize all these different components for any given model of rocket and rocket motor that you want to pair it with. And with all the information that this is, again, you can take, give me the position at some time interval, time step in here, and you can take all that information and put it into your own application. Maybe you use that information and create animations on top of Google Maps or something. For here's what we expect our rocket to do once we have shot it. I find it fascinating and very easy to use, as we saw here. One last thing I will bring up. So I'm not these power on and off drag curves. I wasn't able to find too much information about it. I'm sure you can get it from the manufacturer. However, for the actual thrust, for the motors, there is a open source website. Just look for rocket thrust, solid rocket thrust curve. Here we go, thrustcurve.org. And this will give you the thrust curve in that TSV format that you need in order to use this library. So just going home, search motors, or just what is the most popular motor? Probably what is the easiest you can get your hands on. So let's say let's just use this one here. So we got a bunch of information. The average thrust, its dry mass, and all of that, and we have the thrust curve right here. Now, if you want to use this on your own, you download this RASP format. RocketPy is asking for a CSV, TSV, or this .eng format. Here's the raw data. You can just copy paste this, but you just download it and just replace the information. You don't need the header there. You can just grab this information, and then RocketPy can use that particular thrust curve. You could even play with the thrust curve if you wanted to. If you were designing a new rocket, like what is the optimal thrust curve for the body of rocket that I'm using, and then go out and find a rocket motor that best matches it. Something like that. Okay, so that is RocketPy. I highly recommend just playing around with it. You can do that in Colab because they have a link on their README. Like, I'll just click it open right now. This is pre-made all by the developers. You can see it's their getting started guide, more or less exactly what we just went through, including the simulation stuff, just using the static margin of the fins rather than the rail buttons that we just did. And all of this is running on Google servers. It even will do your pip installs and downloading all of the data files that it needs. And it's great. You don't have to worry about installing anything. As long as you have a Google account, then you can run code in the cloud. Say Microsoft and other companies have the same sort of thing. Highly recommend it if you haven't tried playing around with cloud code execution. But that is RocketPy. I hope everyone enjoyed this talk, and if you have any more questions, put them in the chat. For that, thank you for coming out.